for attending the Delivering Great Performance and Battery Life session. My name is Sharif Faraj, and with me is Jason Hendrickson, who will be presenting today as well. We're on the Windows Performance team, and part of our role within the Windows development cycle is providing guidance and optimization opportunities across all feature teams in Windows on how to design for great performance and great battery life. We're going to share with you some of the concepts and approaches that we've taken in Windows and some of the capabilities that are there in Windows 8 on how we've designed and engineered Windows 8 for delivering great performance and battery life across the spectrum of PCs in the time frame for Windows 8. So we have about an hour today. Please turn off your cell phones just because we're videotaping, and we're gonna present for about 45 minutes. We'll take Q&A at the end. There's microphones in the center so that you can come up and ask questions. As always, we'll be here after the session as well if we run over, so that you can ask those questions outside as the next session sets up. So the agenda, you guys have heard a lot during the conference already about the expanding range of PC capabilities. We're going to spend some time drilling into that a little bit more and understanding what are the implications from a performance and power perspective as we see the range of PCs growing ever more so than ever before. We'll talk a lot about the concepts and how we've approached Windows 8 development from a performance and power perspective. Talk a lot about the capabilities that exist for you as developers, as system integrators, to take advantage of these capabilities to drive great solutions in the Windows 8 timeframe. Hopefully you'll leave with a great understanding of why Metro-style apps have been designed from the ground up for great performance and great energy efficiency. We'll talk a little bit more about that in more detail. How to take advantage of Windows 8 features. We've built a lot of features and capabilities. You'll see that not only do we look at the operating system and delivering great performance and battery life, but how do we provide solutions and capabilities that you as developers can take advantage of as you're delivering solutions in Windows 8. And then tips for delivering great experiences across the broad range of hardware. So first, let's drill a little bit more into the expanding range of PC capabilities. Expanding the range of PC capabilities, you saw a lot about in the keynote. Mike Ann showed this broad range of PCs from the very Windows 8 tablet time frame all the way up to the 3 graphics cards booting up in less than 5 seconds. The range of PCs in the Windows 8 time frame is going to be greater than ever before, and that's a great opportunity for you as developers, but also poses challenges that we have to think about. So we'll talk a lot more about that. Obviously, historically, there's been a big range of performance and power capabilities as we look at desktops, laptops, and all-in-ones. What we're seeing is a trend of thinner and lighter PCs. Customers are demanding and expecting longer and longer battery life year over year without compromise to performance. And that's kind of one of the big things that we're going to be talking about is how to deliver great battery life, how to deliver great energy efficiency without compromise to performance. If you look at the capabilities from processing and graphics, there's a lot of power and headroom. We're talking, hundreds of watts on various PCs today in the marketplace, down to milliwatts, and we're really thinking about low power components. Innovation continues to happen on the high end from a performance and power perspective, and we can deliver great experiences on the high end segment. But as we look at the low power segment, it's really about delivering great battery life without compromise to performance, and the innovation that's happening with silicon partners and delivering great battery life without compromising performance. There's implications there for us as developers, both from an operating system and an application perspective, and we'll drill into that. If you think about the idle power states, you've heard a lot in a lot of the keynotes about this new power state called connected standby. I'm not going to drill into it in this session today, but I encourage you to stay after. Pat Steeman's delivering a session on connected standby and how we've looked at designing connected standby from an OS perspective. This poses challenges for us. It poses great opportunity, but challenges as well. Applications can now feel alive and up to date all the time, but how do we deliver those great experiences without compromising battery life? And so we'll talk a lot about the implementation details of how we've delivered that and some of the capabilities to enable this great experience without compromise to battery life. So one of the key messages here about this broad range of the PC and where it's going to look like in the Windows 8 timeframe. It's clear that innovation is going to continue to happen, and the segment and the number of devices that Windows will be able to run on is greater than ever before. This is a snapshot in time and what we're looking at. We can't imagine what the Windows 8 timeframe is going to look like in terms of the number of the PCs that we can run on, the capabilities, the sensors that are available. Just amazing range of PCs that we're going to be able to target in the Windows 8 timeframe. But with that, we can't rely just on continuous performance improvements year over year. We really have to design the operating system, the applications to really deliver those great experiences without compromise to power and battery life. The good news here is really the engineering best practices that we're going to talk about and the concepts of how we've looked at performance and power are no different than what you're all familiar with. The key thing, though, is it's more critical now than ever before to really focus on these engineering best practices. The optimization techniques are very similar, both from a performance perspective as well as from a power perspective. You're very familiar with all of these performance optimizations. It's really no different if you think about from the Windows 8 tablet time frame all the way up to servers, the amount of resources that you use, how frequently you wake up. All these things matter across the entire PC ecosystem. It's very critical as we expand that range of PCs that we focus more on this. In the end, as an app developer, you have the ultimate choice. You can choose the range of PCs that you want to target. You can go for the broadest range, and I think as an application developer, or if you're writing a solution for Windows, you want to target the broadest range possible. With that comes considerations that you'll need to take into account, and we're going to spend some time today talking about that. So your app's ability to perform well across the spectrum of PCs is going to enable you to reach an increasingly broader audience. So next I want to spend some time talking about how we think about this. What's the model? What do we, when we talk about performance and power, how do we approach this? When we think about performance, it really comes down to minimizing consumption. The activity that you want to do, when you're doing that activity, how do we minimize the resources that we use? Every single one of these devices now has a large power range, a large performance range, and the ability to minimize resources across the system enables great performance as well as great power. So in a lot of cases, what we often tell teams is drive performance optimizations, reduce resources. That's going to help both from a perf and power perspective. Prioritizing UI responsiveness. This is another key concept that we drive a lot with during Windows development. Focus on the work that's critical to get done during that scenario. And we spend a lot of time looking at various scenarios across the operating system. Things like application launch times. Minimize the amount of work that needs to be done to really complete that scenario, to deliver on that experience, and then delay the other stuff that's not critical to deliver on that. Scale at runtime to various hardware characteristics. Understanding the hardware capabilities. And just an example of this is we're running from single core machines all the way up to 8 core, 16 core machines on the client side, and learning how to take advantage of those cores within your application so that your application scales and delivers greater experiences, and is able to take advantage of the horsepower underneath you. As I mentioned, on the power side, it's really about minimizing consumption. That's one key vector that we look at. How do we minimize the resources that we're using to complete that task that the user wants to complete? But it also is about waking up. How often do we wake up? And we'll walk through a lot of the investments that we've made to not only improve the frequency of wake-ups across the OS, but provide mechanisms for application developers or system integrators to be able to take advantage of this, to really minimize how frequently we wake up the system. And at the end, it really comes down to stop running when not needed. We'll talk a lot about the suspend model that we've enabled in Windows 8. How do we deliver that multitasking experience and that look and feel of multitasking without compromise to power and performance? And so we spend a lot of time really, when the application moves to the background, how do we minimize that activity completely across the operating system? So this isn't intended to be a feature rundown of all the things we've done in Windows 8. What we wanted to do is spend some time talking about specific features that we've enabled around performance and power. We're going to spend some time talking about the great performance improvements we've made with HTML to enable you as app developers to take advantage of those performance optimizations. This morning, Ben Strower delivered a talk on the process lifetime management and how we've enabled this great multitasking experience for you to take advantage of, but without compromise to power and performance across the spectrum of PCs. We've also built capabilities into Windows 8 and features into Windows 8 to reduce the need for startup applications. And we encourage you to really look at that. We'll spend some time talking about that today as Jason talks through these features. And you see that we've really looked at every single resource across the system. A lot of these resources in terms of driving CPU, GPU improvements. And we've also looked at disk. How do we minimize the amount of I/O that's happened across the entire OS at any given point in time? So we spent a lot of time looking at that and minimizing I/O across the OS completely. I think you guys all saw Steven Sinofsky's show, Memory Footprint of Windows 8. And we're not done there, but one of the things that we've done is really focused on delivering all these key features, delivering an anti-malware solution, and doing so with less footprint than Windows 7. A great starting point from which we started from was Windows 7, but we've driven more memory ejections across the OS. And there's a talk on Friday that I encourage you to come to and hear about the impact of memory from a responsiveness perspective, how memory impacts responsiveness on the system. So I encourage you to attend that talk on Friday. Finally, from a power perspective, we started this journey back in Windows 7 in terms of reducing the amount of wake-ups in the system. We continue that work through Windows 8. Timer reductions, removing those things and moving more towards an event-driven solution in a lot of cases. Providing mechanisms both for OS developers, but also you as application developers to coalesce activity so that when we wake up once and do that activity and go back down to low power idle states. And then we've also implemented resiliency features so that when we get into this connected standby case, we really try to minimize the amount of activity that happens. And we wake up very infrequently to do activity, get those applications to feel alive, but go back into a low power state as quickly as possible. So with that, I want to introduce Jason Hendrickson, who will walk through and spend more time talking about the details of these.
Thanks, Sharif. So Sharif has talked to you already a bit about the high-level approach and some of the features that we've taken into account with Windows 8 to try to deliver on consistent, great performance and battery life. What I want to talk to you guys today about is how we put those kind of into effect, how we put those in motion. Talking from the high level is a good start. But what we wanted to do when we went into Windows 8 development is we wanted to look at the platform-wide approach. And what that meant is that we're not just looking at Windows. We're not just looking at the hardware. We're not just looking at services. We're not just looking at apps. We're looking at everything that runs on the system to make a great Windows experience. And when we did that, we noticed that there was a number of platform-wide things that could be done that don't just touch on one resource, reducing CPU consumption, reducing disk consumption, et cetera, but that actually help improve across the board the consistency of responsiveness and the consistency of battery life that people want to see. People don't want to see one day they go through, everything performs fine, and then for about a half hour, will they really want to get something done? The system bogs down. People don't want to see that. People don't want to see, I have great battery life today. I can get all the work done I want in a day, and then the next day, my battery dies halfway through the day. People want to see consistency of great performance and consistency of great battery life. So what we started with is looking across the board at what can be done to make sure that they get that consistency across the set of resources that comprise the hardware system and the user experience. So let's start with suspending apps. So if any of you attended Ben Schrower's talk this morning, he talked about some of the motivations behind the new Metro-style app model and the process lifetime management that's going on in the system. So across Metro-style apps, these have been designed by default to enable great experiences, a feeling of up-to-dateness for the end user, while at the same time not requiring the apps to run all the time. There's a lot of facilities that have been put in place to ensure that you can deliver a lot of great experiences with Metro-style apps without having to run all the time. With desktop apps, we want to enable the breadth of desktop apps that exist today in the PC ecosystem to continue to run. We'll talk about some improvements that we've made that hopefully will enable you to switch over to the Metro-style app model. But with desktop apps, even then, we wanted to make sure that when we enabled this new connected standby state that's different than traditional sleep, we wanted to make sure that great battery life could be achieved. So in the Metro-style app model, the OS manages any activity that happens in the background, meaning that if your app isn't in the foreground, and you need to run in the background, there are certain facilities to do so in a limited manner. So you can deliver the experiences you want without your app having to have threads that are in a running state at all points in time. With desktop apps, what we did is we wanted to make sure that desktop apps could deliver the breadth of experiences that everyone's used to today, but that in connected standby, which again Pat Steeman will talk about in the session after this one, where some parts of the system stay running to make sure that users can stay up to date, that in connected standby, battery life is maintained. So with desktop apps, those are suspended when the system enters connected standby. With Metro-style apps, they're suspended a lot more often so that they can be suspended but still deliver the kind of battery life and performance expectations that everyone's come to want out of Windows. So, we talked about how Metro-style apps can help improve the system performance and battery life expectations of users by just not running as often. Startup apps are still there. That's something that everyone's familiar with today from traditional PCs. What we wanted to make sure is, okay, where possible, we created facilities in Windows 8 such that you don't need to depend as an app developer, as a system integrator, on startup apps to deliver the kind of experiences you wanted, so that more apps could migrate over to that Metro-style app model, where there's a lot more protection for consistent battery life and performance. First thing we did is we took a look at the Metro-style app model, and we took a look at some of the startup apps that people use on the system, and some of those are to keep the user always feeling up to date. Some of those are your IM apps that just start up at system startup. They put themselves in the system tray. Some of those are VoIP apps that start up, put themselves in the system tray. The Metro-style app model actually provides better ways of keeping users connected and up to date. Better, consistent ways to make sure that user data can appear on the lock screen, toasts can pop up when things happen, very consistent experiences. So we encourage you to think about using the Metro-style app model when developing apps of this genre. Automatic maintenance was something that we developed to ensure that where there are maintenance activities that need to take place, and today may be served by creating startup apps, that you're able to actually take advantage of automatic maintenance to not create a startup app and instead have a task which runs at a time that is optimal for the end user in terms of both battery life and performance. So if you create a maintenance task, the OS does what it needs to do and does what it can do to make sure that the user doesn't have to see it. So where you want to deliver experiences of up-to-dateness of applications, up-to-dateness of any maintenance that you want to perform, you can do that by taking advantage of automatic maintenance. And again, this means that you don't have to be persistent in memory. You don't have to have boot impact. You don't have to have power impact because of anything that might be going on in your app to check. In addition, for hardware-centric apps, which today may be always running, maybe just run on demand, there's a lot of facilities that have been put in to make the Metro-style app model appealing. One of those is that if you have a hardware-centric app, that hardware-centric app can be automatically downloaded from the store if a user plugs in the device to their system. So transitioning to use Metro-style apps can buy you a lot in this area, and we encourage you to explore what you can do to reduce any dependencies on startup apps to make sure that users, again, get that consistent battery life, consistent responsiveness that users can get when stuff isn't just running in the background on their systems. So I wanted to take a step back then. We talked about how you can make it so that things don't need to run on the system at all times, but users still get the battery life and performance that they want and the experiences that they want. So what happens when something is running on the system? How can you make sure that performance and battery life are optimized? Well, one of the ways that we look at it is, as Sharif mentioned, for battery life especially, you don't want to wake up the system continually and repeatedly. One of the ways of doing that is just reducing timers across the board. If you can make whatever you were doing to wake up on timers, if you can turn that to being event-driven, such that you wake up only when the system's already awake and only when there's something for you to do, that's the first step. Try to reduce timers across the board. What happens if you need a timer, though? Well, this is where coalescing comes in. As you can see here from that first example over there, frequent wakes often, for different devices, create an inability for that device to enter low power states. And what this means is that even if you're not doing much work, frequently waking up means that power consumption overall on the system can be higher. What coalescing enables is for all this activity to happen at once. So if you don't have strict needs of needing to wake up at a given point in time to deliver the experience you want to do, you can coalesce to a certain tolerance, which means that the OS can say, hey, if I'm already awake, run. If I'm not awake yet, don't run for a little bit longer because the app, the service, doesn't need to wake up immediately. It can batch those up, and what you see here is you get a lot more idle time, a lot lower power consumption. So across the board in Windows 8, we worked to make sure that timers were reduced across the board. That when we wake up in a batched sort of manner. And this happens across a number of things. You may have seen in your usage of the Windows 8 tablets that were handed out, you may have seen that, yeah, tiles remain up to date. They keep users fresh with content. That happens in a batched manner. Stuff that's coming in from the cloud for notifications, that happens in a batched manner. Batching things helps in a lot of ways to reduce power consumption while delivering the experiences that end users want. So there's a lot of best practices talked about here. I think we covered a number of those, but again, the key point, be event-driven when you can, remove timers when you can, coalesce timers to large bounds when you can, and don't have persistent timer wakes. For example, persistent animations in general aren't great for battery life. Batch what you can. This buys the user, in general, better power consumption. Fewer CPU wakes, less time in high power states, better power consumption. Coalescing makes it so that when you wake up to do minimal activity, you don't need to have a large power impact on the system. You can still get the work you want done. So we talked a bit about power. We talked about general broad responsiveness of the system. Starting here, we're starting to break it down into more fundamental areas. Now, one key thing to note about all the content that's going to happen here is performance isn't one of those areas where anyone can just stand up here and talk for 30 minutes and convey everything. So obviously, there are a number of references for a number of additional sessions that you can look at here. What we want to do is we want to introduce you to some of the high-level key topics that we thought about when we were developing Windows 8 to make sure we could deliver a consistent experience, a great experience, across the different hardware resources in the system and across the different app models in the system. So what you see here is that we spent a lot of time focusing on enabling great performance with Metro-style apps that are developed using HTML and JavaScript. Now that's not to say that C++, C#, XAML are any less optimized. You guys already know the great things you can do with performance in C++, the great things you can do with performance in C#. What we want to do here is talk to the point that, yeah, HTML, JavaScript, first-class citizen. We've worked very hard to make sure that the performance of it isn't a second-class citizen. You can deliver great experiences with these, and it can be performant across a breadth of hardware. We built on the IE engine. And as you guys are all well aware, starting with IE9, there was huge leaps and bounds in terms of improvements in performance. And that's continued with IE10. So building on the IE engine starts us off from a good spot. In addition, WinRT, the Windows runtime, has done a lot of work to make sure that long-running operations happen asynchronously. These don't have to block you in JavaScript. Even though JavaScript by default runs single-threaded, you don't have to be blocked waiting for disk I/O. You don't have to be blocked waiting for network or waiting for cross-process calls. You don't have to be blocked. You can keep the UI responsive by using the asynchronous calls that are built into WinRT and using what's called the promise for WinRT. And there's, again, a number of additional sessions which will get much more into detail on these. Touch and animations is something that I believe Jensen touched on in his talk yesterday, where the OS, by using OS controls and by using OS mechanisms, enables you to take advantage of really optimized touch responsiveness and really optimized animations. So by using a number of the facilities that we've built into the Windows runtime, you can, again, deliver great consistent performance, touch, and animations, and you don't have to worry about it. So we've done a lot to make sure that you can do a lot of things and don't have to worry about micro-optimizing. And in addition, via web workers, you can parallelize across cores. So this is what Sharif was alluding to when he was talking about you're going to run across a breadth of hardware. You don't know how many cores you're going to run on. With web workers, what that enables is for you to get work that's not necessarily critical for the UI to be responsive. It can be parallelized off, and it can happen across cores if they're available, or if they're not available, it can happen in a way that still keeps the UI responsive to user input. So there's a ton more that each of these sessions will talk about. You see 50 performance tricks. I've enumerated 4, so obviously there's a lot more to talk about there. But we just wanted you guys to be aware that building with HTML and JavaScript doesn't mean you have to be second class in terms of responsiveness as felt by end users. So we've talked about the app model. We've talked about system-wide things that could be done. We've talked a little bit about power optimizations. Let's talk about disk. We'll talk about memory. We'll talk about network in slides that are upcoming. So when we took a look at Windows 8, and we took a look at what we wanted to do to ensure that the disk always felt responsive to end users, what we wanted to do is we wanted to make sure that the foreground app always got the disk access that it needed, or as much as possible. So what we did there is we looked at Windows, looked at what kind of things were happening on the system, and we immediately said, okay, we're going to drive down disk IOs. And we drove disk IO improvements in many key areas. One of the key things here is that if it's not in service of something in the foreground, why does the disk IO need to be happening? We took a look at that across the board. And when it does need to be happening, why does it need to be happening in a way that's going to get in the way of foreground IOs that need to happen? And so what we did is we changed the system to write at low priority by default. What this means is that by default, writes that happen on the system unless they're explicitly flushed to disk or unless they're explicitly marked as unbuffered. These will happen at low priority, meaning that if something comes up in the foreground and needs to read from the disk, needs to read from the page file, needs to read a DLL, needs to just read to service the user expectations, it can do so without writes getting in the way. Now, of course, if you have very, very strong reliability requirements, you can still flush. But what we've encouraged our own developers to do is think about the 99% case. And if, for the most part, you don't need to flush, or for the most part, if you run into reliability concerns, you can go and you can recover that when it happens, and you can still deliver a great reliable experience, we've encouraged people to think in terms of that, rather than proactively flushing just to make sure things happen on the disk. By not flushing, you get low priority writes by default, you make sure that the user gets foreground responsiveness by default, and you make sure that when the screen's off, we can actually coalesce those writes, make them go out to disk without having the disk have it spin up all the time, every single time a write comes up. And so we believe that you can do great things by default if you just let Windows manage the disk writes. Memory is something that Sharif talked about a bit. Memory is something that Steve Sinofsky talked about a bit. Memory is something that our team has spent a large amount of effort on to make sure that it's respected consistently across the system. Now, you've seen the kind of memory reductions that the Windows team over at large has delivered across Windows 8. And again, as Sharif mentioned, we expect to continue to improve things there. As an app developer, what you can do is you can minimize memory consumption. We believe that a good experience across a number of apps can be delivered on the order of magnitude of 50 megs. Now, this, of course, will vary, but it's something that a developer can strive for, delivering a good experience without high memory consumption. What this really buys you as an app developer, especially as a Metro-style app developer, is, again, if you attended Ben Schrower's talk this morning, you're aware that processes can be suspended when you're in the Metro-style app model, but you can also deliver the kind of great experiences that you want. If you're suspended and your memory consumption is high, and memory is needed by the foreground app, what Windows does to serve the user is it can terminate those background applications that are consuming a lot of memory. The app gets its time to write stuff out to disk, to save its state, all that kind of stuff. But the implication this has here is that as an app developer, you're serving your users better if you consume less memory, because when the user wants to switch back to your app, it doesn't need to be relaunched if you're not terminated. If it doesn't need to be relaunched, that means much better responsiveness for the end user. And so that's something that's a key benefit to reducing memory usage, apart from being a great citizen on the system. If you have high memory consumption in the foreground, that means that the user may need to have fewer apps running in the background, and the system may terminate apps to make room for you. So memory is great. Reducing memory consumption is great for being a great citizen on the system, and reducing memory consumption is great to reduce your own app's likelihood of being terminated. If you're writing a desktop app, really need to be cognizant of memory consumption as well, because you're not living in the Metro-style app model. You're assuming the user is going to do the process lifetime management, as Ben Schrower talked about this morning, and it's critical to make sure that when the user switches back to your app, that the memory consumption was low so that you can be switched back to in a responsive way. One additional thing we did here when we approached Windows 8 development is we stopped a number of services when they're not in use. We made sure that service startup was really fast. Service startup could happen on demand. And services could be stopped when they're not in use to make sure that they didn't have a resident memory footprint. And that's some of how we delivered on some of the improved memory footprint that you've already seen. So we encourage, again, when you don't need memory, stop using it. If it's easy to recreate memory when you're switched back to, then why are you holding on to that in the background? Think in terms of that, and you can improve the user experience for the end user. And again, as Sharif mentioned, there's a session this Friday which gets into how to identify opportunities from a memory perspective and how to drive optimizations. So network. We've talked a bit about app models. We've talked about responsiveness across the system. We've talked about power across the system. We've talked about a couple of resources. Network is one of those that you guys are probably very familiar with. I'm sure all of you have experienced apps that wait for the network on the UI thread. And when they do that, the app is just not responsive when you have not great network connectivity. Not assuming network connectivity is great is a great start towards developing a really performant app. Probably all you guys know that. There's some additional facilities that we've built into Windows 8 to make sure that network is even easier for you guys to use in a performant, power-efficient way. The first of those is the background file transfer API. So the background file transfer API uploads and downloads to your backend using HTTP, even when Metro-style apps are suspended. We don't get into how to use this. I believe there's another talk on it, but Ben Schrower, again, covered that in his morning talk on process lifetime management. Using asynchronous calls, using background file transfer APIs, that helps you to optimize your impact to foreground responsiveness. Make sure the UI stays responsive. You've put the network calls in the background so that you can deliver the experience that end users want. And something that we saw a lot of in the Windows 7 timeframe is that there are certain apps that kind of pull for connectivity, pull to see if they can connect to their backend. In Windows 8, there's a connectivity change API you can use to get notifications that network has changed and that you may need to reconnect to your backend. So instead of polling, instead of using resources, instead of waking up to do that, you could take advantage of the connectivity change API so that you don't need to poll. There's another session that goes over these in more detail, and that's given in the appendix. So we've talked about a number of resources on the system. We've talked about general power consumption and how the app model has changed to make sure that power consumption, responsiveness are to the default. What we want to talk about a little bit here is in Windows 8, how we approach development, how we approach responsiveness. So what we did is we took a look at users, and we took a look at their expectations of responsiveness. And as Sharif alluded to, users have an expectation of responsiveness regardless of the underlying hardware. Yes, the underlying hardware definitely plays an effect on how fast things are. That's, of course, true. But if users are running across hardware that's lightning fast and hardware that's less fast, that doesn't mean that they don't feel that there's the same speed requirements. Or, put another way, if they're using a system where, for whatever reason, things are slow, they still feel slow to them, regardless of whether they bought a piece of hardware that was cheaper. So what that means is that user experience is the same across hardware. We want to deliver Windows 8 quality, Windows 8 responsiveness across a breadth of hardware. How we do that is we set goals for key interactions. So we recognize the breadth of hardware we're targeting with Windows 8. You guys can do the same with your apps. You can recognize the breadth that you're targeting with your apps. We tested to ensure that performance, a level of responsiveness, was delivered across that breadth of hardware. We tested across a number of hardware systems. We identified the key scenarios that users are going to have expectations of responsiveness around. As Sharif mentioned earlier, there's a start pane. If that first frame of the start pane swiping in, if that doesn't happen really quick, the user feels the responsiveness impact. And across platforms, regardless of their performance capabilities, if they're capable of running Windows 8, we want that to be lightning fast. So we set really aggressive goals there. Across other scenarios, maybe users don't have an expectation that it's lightning quick. Maybe they just want it to be feeling responsiveness. We set goals there. The goals were elapsed time. The goals weren't CPU consumption. The goals were elapsed time because that's what users end up feeling. And so what we did is we instrumented our code with start and stop events across the board. There's hundreds of these scenarios. Start happens when the user first enters that input that triggers an activity. End happens when the user gets the feedback that they expect out of that activity. You guys can do the same. You can use ETW, event tracing for Windows, for your C++ and C# apps. Or you can use MS Write Profile or Mark for your Metro-style apps that use JavaScript. Once you've instrumented, measure, look at the elapsed times, look at what's causing the code to take a while in between those if it's not meeting the user expectation goals, and optimize performance. And the Windows Performance Analyzer, which we don't cover here but is covered in separate talks, Windows Performance Analyzer is our main tool for looking at what's consuming a lot of resources and what can be optimized within those. So I encourage you to take that talk on Windows Performance Analyzer. I believe it's happening later in this week. So going back to it, to recap at a high level, 3 key things you can do. First of all, Metro-style apps have been designed from the ground up to enable great performance and power citizenship by design. That means that when things are in the background, power isn't being harmed, performance of the foreground isn't being harmed. Developing Metro-style apps ensures that the user gets that promise of responsiveness and battery life across the board. You can take advantage of Windows features to deliver great power and performance across platforms. We talked about those from the disk perspective. We talked about some of those from the HTML and JavaScript perspective. There's a ton of these across the board. And so we encourage you to, as you're looking through the API set that you're being exposed to today, look for the performance opportunities that are there across the board. And then deliver great performance across a breadth of platforms that you're targeting. Tests across these platforms. Keep them in mind when you're developing to make sure that you are opening up your app, you are opening it up to the largest possible audience to make sure that you can deliver on the performance expectations, the battery life expectations that users are going to have, and users are then going to want to download the app more often, want to buy the app more often, etc. So again, as I mentioned before, this is just a high-level coverage of our way of thinking about this, the breadth of features that we're providing, and there's a ton of other sessions which will help you out to understand the Windows platform better and understand optimization techniques better. This is just an introduction. Understanding Connected Standby will be the next session. It'll be here starting in 45 minutes or so. Fundamentals of Metro-style apps, that was delivered earlier today. This is talking about suspending apps and the kind of up-to-dateness you can provide with your apps. The memory footprint in drivers and apps, that talk tells you how to optimize for memory footprint. The building high-performance Metro-style apps using HTML5 and 50 performance tricks, that gets you into how to optimize the performance of your HTML5-based apps. And then the number of the sessions below talk about network and delivering apps for great hardware-based apps. So with that, again, high-level overview. Want to open it up for questions. Sure if you want to head up. Oh, yeah, there's a mic there if you want to head over. Sorry, the lights make it hard to see who's raising their hands.
You mentioned that services are put into a throttled mode. Could you describe what throttled means a little bit more?
Sure. Throttling, so when we enter into the Connected Standby, there are various services in the system where we will give them time to run for, the policies haven't been locked down here, but we're thinking, as an example, I'm just throwing out an example right now, well, you'll run for 1 second every 10 seconds, as an example. A lot of the thinking in this space here is that while we're in Connected Standby, there's nobody there. And you'll learn more about this in the next session, but the screen's off, the user's not there at their machine. So that work isn't really that critical to complete at that point in time. So we spent a lot of time thinking about that and looking at the services from an OS perspective and understanding what are the services that are core to keeping that content fresh and alive on the PC, and services that aren't critical to run but may need to run for other reasons. We time slice those things and just give them a little bit of time to run and then get back down to an idle state. So that's we haven't locked on the policies in this area completely, so I don't want to throw out what numbers those look like, but we're going to be throttling those services that aren't critical to delivering that Connected Standby experience.
Yeah, and one key thing I want to add to that is that there are a number of cases in which things are running on the system. So for example, as Ben Schauer talked about earlier today, you can still develop apps, Metro-style apps, that remain connected to the back-end services that they provide data from. They still remain connected, even in Connected Standby. And so Pat Steeman will talk a lot about that. But the idea there is if those are executing something, they might need your service. And responsiveness is critical, actually, to the end user there. If there's an incoming IM, an incoming VoIP call, responsiveness is critical there. In those cases, the services move out of those throttled states. In the case where a user presses a button and powers on the screen again, services come out of those throttled states. So there's a number of cases that are responsiveness critical where services do come out of those throttled states.
So one kind of common scenario today is, before I leave work in the evening, I'll kick off something that I know is going to be kind of a long-running, CPU-intensive thing. I'm hoping for results in the morning or something. How is something like that going to get suspended when I've been away from my computer for however long? Or, how will something like that get managed in Windows 8?
Excuse me. So everybody heard the question. So there are certain scenarios that will be able to run with the affordances that we've talked about through the Metro-style application model. Other activities like that where are actually applications that are doing that are actually more accustomed to eventually going to sleep, where the PC is actually going to go to S3 on. And so we believe that to enable those type of scenarios, we really need to do so using Metro-style applications. And so there are affordances there through the background activity that we allow to run during those scenarios, and we encourage developers to really think about those and take advantage of the Metro-style application model to deliver those same experiences without compromising on power, without compromising on energy efficiency on the platform.
Yeah, and actually let me give just a couple additional notes. So A lot of stuff that happens for connected standby, again, the policies are still being locked down upon. But a lot of stuff that happens for connected standby doesn't necessarily apply to platforms that don't implement connected standby. Connected standby isn't a state that exists on the breadth of Windows PCs. It exists on Windows PCs that are capable of achieving really low power consumption while they appear to be off, but can still remain connected, for example, to backend services. So it's a class of PCs that implement connected standby. And in addition, some of the Metro-style affordances for suspending apps, those don't apply necessarily to desktop apps. So for example, if the case is I'm compiling on my quad-core desktop, and I've disabled sleep on my quad-core desktop, and I'm doing that using the command prompt or using Developer Studio, which is running in the desktop. If that's the case, no worries. That continues to run. So it's really that the suspension of desktop apps and the throttling of services, that applies to connected standby. Whereas on PCs that don't implement that, it's not a concern for you.
Could you come up to the mic, please?
Yeah, sorry about that. This is being recorded, so we want to make sure everyone gets the benefit of this.
What about systematic and where it's changed, it's not 16 milliseconds anymore, and where it's dynamically changed with the load of the system? And if yes, what is the impact of it on the timers of applications?
So yeah, so in Windows 8, the system timer no longer ticks by default at 15.6 milliseconds. That doesn't mean that you don't still get the same resolution of timers that you might need. That means that if there's nothing to wake up every 15.6 milliseconds, the system doesn't wake up, because all it would do is wake up, check a table, go back to sleep. Or not sleep, but I think you get the gist. So what that means is if you set a timer for 3 seconds out, and if you decided to not coalesce that, although we encourage you to coalesce it, it could still wake up at that 3 seconds. It's not kind of bound, at least when the screen's on, it's not bound to any additional intervals. Now, when the screen's off in connected standby capable PCs, there's some different stuff there, because as mentioned, desktop apps will be suspended and services will be throttled. But in general, we're not doing anything to make it so that you can't achieve the level of time resiliency you want. But again, encourage coalescing activity, and we believe that most activities don't really need to change the timer resolution from the default 15.6. You can get great animations and all that kind of stuff with 15.6 millisecond resolution. So.
This one's working as well, I guess.
Apparently.
So on the disk access minimization, you're talking about doing some coalescing at the operating system level. Can you comment a little bit more detail what sizes, what scope of deferring you're planning on doing? Are you targeting like 1 megabyte chunks, smaller? What are you targeting?
So the deferring isn't really necessarily happening on a size level. What's happening is that for a certain period of time, if no one decides to go down and flush the disk, for a certain period of time, those writes are just held in memory. Now, because memory, consumption could increase significantly if too many writes are held in memory, at a certain point, there will be a memory threshold that's at which it says, hey, I'll spin up the disk if it's a rotational disk, or I'll turn on the disk if it's just in low power states, and I'll write that out. But otherwise, it's not limited to specific I/O sizes. So if you write in small 4K chunks, or if you write in larger chunks, 64K and up, it'll be held in the same manner.
Yeah. So and a lot of a key point here is like that the policy decisions around those features are still being worked on. So anything we talk about today, we're still fine tuning those policies on how long are we going to coalesce for, because as Jason alluded to, there is a memory cost associated with the amount that we batch or the amount that we coalesce. So we're still fine-tuning those as we look at the platforms that we'll be targeting.
Well, one key thing to know is if you read from the disk, it's assumed, yeah, that's pretty important because you need to service that read to make further progress. And if you flush to the disk or write in a write-through way, it's assumed, again, yeah, that's pretty important. It's got to get to the disk. Other things can be deferred a little bit more.
Sorry, can you go to the mic?
Sorry about that.
So we saw earlier today about how easily you can write for Windows Phone as well as for the tablet. Mm-hmm. If Windows Phone is your primary use case and the tablet is secondary, would you write any differently?
Well, the Windows Phone platform and the Windows tablet platform, they are different code bases. A lot of the same principles still apply. I'm not sure that you or I can talk to any of the background or.
Yeah, I mean, I think the same principles still apply in terms of how frequently you're waking up, how frequently or how much activity you're doing. Haven't written an app for the Windows Phone, so I don't want to comment on that, but the concepts are the same. It's a lot more. One could argue that it's a lot more critical on a phone device where you've got a much smaller battery, and so the impact is larger. But the concepts and the best practices are very similar across all platforms.
Hey, so you mentioned a lot about optimizing system I/O and disk I/O. So how much of the principles that you described apply to graphics as well?
Graphics. So graphics definitely. I think that the reducing consumption definitely applies. When you're talking about graphics is a complex space because it involves CPU and GPU a lot of the time. CPU wakes up, triggers some activity on the GPU, GPU does work, goes back to sleep. And GPUs have a really, really, really broad array of different capabilities. Some of them use system RAM, some of them don't use system RAM, some of them use their dedicated RAM. So they have a really broad array of capabilities. And very astute of you to point out that GPU is missing from this slide deck. Reducing consumption definitely applies there. And in terms of the work that you do, since a lot of components wake up to do graphics work, batching also applies definitely in terms of a power impact there.
That's brilliant, yeah.
And we can talk afterwards if there's anything specific that you want to.
Any other questions?
In case this doesn't overlap with the next session, on the standby or the always connected model, you're looking at minimizing waking up some of the peripherals that would have to be woken up. As far as the disk access, are you envisioning a scenario where you would not even spin up a disk in the standby mode?
Yeah, I mean, in terms of connected standby, we're looking at really, really, really low power consumption, so we expect solid state to be much more, common there. In terms of actually getting disk IOs out and whether it's spinning up, whether it's just powering up devices, again, as mentioned in the previous section on disk, there is disk coalescing. It's in play when connected standby is entered, but even in connected standby, so much is suspended that the idea is that disk IOs probably shouldn't be initiating anyways in a bulk level. So our hope is that disk IOs aren't being initiated. It's coalesced when they do happen, so the power consumption is significantly less.
You talked about disk I/O and other stuff, and can you say more about media playback optimizations? Is there any improvements to reduce the disk access?
Media playback in general has been a huge focus in Windows. There's a lot that's evolving in the hardware community around being able to offload work to the device itself, and that's definitely being taken advantage of. In terms of disk access specifically, let's talk a little bit more about that if that's a concern.
Yeah, I'd like to get more detail from you offline if possible.
Yeah, but it's definitely been a big focus.
So you talked about maintaining performance regardless of kind of what the capabilities of the platform are. So it assumingly means that on a better system, our apps should do better or cooler stuff. What's kind of the best way to determine what kind of system we're running on so we can scale up or down accordingly?
So scaling up and down accordingly, in our experience, has been a really feature-specific, app-specific sort of thing. Every feature, every app requires very different things. What we tend to do is we tend to look at it because again, we're developing the Windows platform for the broadest range. What we tend to do is implement that philosophy of prioritizing UI responsiveness and parallelizing as much as possible. So if you're doing that in a way, it automatically scales, because if you prioritize the foreground and a single core or something along those lines, you get that foreground work done, everything else happens in the background. And you can scale automatically to multiple cores. I think we might need to chat afterwards about specifics because, again, it's been like every feature that we've had that question asked about so unique.
So my question is about coalescing activity. It seems that it's a very cooperative, collaborative enterprise in terms of all the participants. Can you comment on the granularity of control? Because it seems that if your process is compliant, then you're only as, I guess, optimal as the least compliant participant.
Yeah, I think put a different way, we often talk about it as we're only as good as the weakest link in the system, right? And both performance and power really do require that good citizenship model. In a lot of cases, I really do encourage you to think about whether a timer is even needed. And when we've engaged with all of the Windows feature teams and we talk to them about the timers that they have in the system, a lot of times they're not needed. They can move to an event-driven model, and that's what we really want to think about first and lead with. In terms of, and another thing is like the way we've designed the Metro-style apps in a lot of ways. When you're in the foreground, we expect you to favor, you're the user's interacting with your app, and so we want you to be able to deliver on the responsiveness. But when you move to the background, that's why, we talked about the process lifetime manager or management and how that app's going to get suspended, so that timers that you may have had aren't actually going to run, that your application's been suspended. And then you use the infrastructure underneath from an OS perspective to say, I need this background activity to be done even though my app's suspended, and we'll align that activity together. So, in a lot of cases, I really encourage application developers and OS developers to look at why the need for a timer to begin with. Is it really needed? Because there's so many different event notifications that are provided within the operating system to get network state, to get display state, and various things, and take advantage of those things, and then cancel timers when once you get those notifications that the display's been turned off.
Yeah, and actually, I want to just add to that that's actually the exact reason why we spend multiple slides talking about suspension policies, talking about the mechanisms put in place to make sure that startup apps aren't needed for certain categories, to make sure that if something's not running, you don't have to worry about timers. And the more and more that migrate out of being long-running processes, the easier it is for the system to have these guarantees to the end user.
Actually, that brought up some good points. So in terms of the Windows ecosystem, I think most people have experienced Windows rot. So eventually a whole bunch of stuff gets added to the system, and there are multiple weak links which bog down system performance. And usually you need to do a lot of work in order to find those processes, uninstall them, remove them from the run once and all that stuff that starts up. And based on the fact that Windows has XPerf and all this information, is it possible, or do you already have an application or a built-in system facility to identify the rotting applications?
Task Manager, I don't know if you saw the keynote on this. One of the new capabilities with Task Manager is you can actually go in, and there's a startup tab now, and you can see all the applications that are installed in the startup path or in the run once key and look at their relative impact across the system from a boot perspective, for example. And you can go in one location and disable those apps. So we've done a lot of that work to be able to enable that. With Metro-style apps as well, this what we call piggyback effect, where you install an app and other apps come along and the user isn't aware of that, it's not really enabled with Metro-style apps. So there's a lot of investments made in various areas to kind of reduce that. We've also, as Jason alluded to, the maintenance mode, right? So you really, in a lot of cases, we see these startup apps that run all the time as being a tax on the system for a user who may or may not need to run that all the time. IAM and VoIP applications, those are exceptions, but having an app simply running all the time to check to see if there's a software update, we really encourage people to really think about maintenance mode where we can batch all that activity together, and so that process isn't constantly running on the system all the time. But in the end, if the user does have that happen, they can go to one location and look to see what are these apps that are constantly running on the system, and how can I disable them from one place.
I guess what I'm trying to say is, does it require a power user to figure this out, or is there some sort of utility that says, here are the problems?
Well, so that's the exact reason why, like, that's one of the key driving goals behind the Metro style app model is the more Metro style apps you have installed on the system, doesn't mean more chance of rot. And so more and more people switch to using Metro style apps, less chance there is there because of some of the protections put in place there. The diagnostic piece, the idea there is that definitely understand the perspective of power user. In this case, we believe the tools are easy enough to use that it lowers the bar. Now that doesn't necessarily say that everyone's family members could necessarily figure out everything, but beyond that, there's additional improvements that we've made across the system from CPU scheduling on up that we believe reduce the likelihood of things like that happening. And we really believe that a lot of the improvements that we've made in the OS kind of protect against some of that happening. So,
any other questions? Oh, we got one.
All right, so a lot of this has been application-based, but from a hardware perspective, I've been, one of the first things I heard you just say was there's hardware dependencies on whether or not Connect to Standby is even supported. So taking that to the next level, there are different types of connections that you can actually maintain on a system, right? There's mobile broadband, NIC, there's wireless. So what kind of impacts are accounted for? Issues can we expect for those different types of connectivities? What kind of impacts do they have on power and performance?
So let me first talk to just the point about there being multiple types of connections. And a lot of work's gone into the OS and making sure that the connection switching is seamless. So we don't talk about that at this talk. We can...
There are talks. I'll pull up I know there are talks targeted around the network investments. Afterwards, I'll point you to those.
Yeah. And so one of the key things is, yes, this has been thought of from the ground up to make sure that that connection switching is seamless. What that means also is in conjunction with the kind of network connectivity change notification APIs, an app can get notification that something switched if it needs to reconnect to its backend. If it's just doing polling on a connection, then that should just happen seamlessly for them.
Even if those switches occur in that
Connect to Standby?
standby state?
Should be seamless, should work great for the user. And again, I encourage you to stay around for the Connect to Standby talk to get more info and all that kind of stuff. But yes, I mean, that's definitely a scenario that we've been thinking through.
So I guess to continue that track a little bit, many applications now require geolocation, to be known constantly. In this sleep state, have you been thinking at all about how you would keep track of the user as he moves around in the sleep state?
I don't know. Is there a broker around sensors? There is, right?
So I know that there's been some thinking around that. I'm not sure if we have a great answer for you today around that. If we can chat with you afterwards, we can at least make sure that we follow up and hook you up with the right people to talk about that. And I believe that there's at least some sessions around sensors and the like. So let's chat afterwards, look at your business card, and we'll point you at the right sessions. Okay. Well, we'll be here for at least a few minutes afterwards if there's anything you want to follow up with us.
And thank you. Thank you very much for attending.
Yeah.